So let's start 7.6. We only have just a few examples to do, and we'll try to keep things basic. So basically we're going to be solving equations that contain radicals. And I talked to you in an earlier email, or even if you're listening to this at some other time, when we have a radical expression, this is the rule that we're going to look at right here that we have to pay attention to. And the rules is what we care about. So let's actually look at this. So here's an example, example 1. We'll solve this in just a second. Notice that the left-hand side is under the radical. The variable is under the square root symbol. And the only way we can get it out is to square both sides. That's the only way we can solve this solution using our normal techniques. So the power rule says, okay, that's fine. If you have an equation, you can square both sides, you can cube both sides, you can raise both sides to any power you want. But when you do so, any solution that is in the original equation is going to remain, but when you start squaring and cubing, you may get additional solutions. So the rule is, the basic takeaway from the power rule is squaring keeps the original solution, but it may add others. And let's remind ourselves of, let's remind ourselves of 3 things about any equation. So any given equation, there's 3 exclusive possibilities. I'll just break it down to 2. 1 or more solutions exist, or no solutions. And this second possibility we often forget about. And depending on the type of equation it is, we expect more than one, but sometimes we only get one. So let's look at example 1, and let's solve it. And I'll show you kind of some preliminary things you can do that will kind of help. So example 1, we're given that 2x minus 3 is equal to 9. And over here I'm going to put on the side note something that's going to be important. Normally I wouldn't even bother to say this, but what happens in section 7.7 requires me to. We are looking for real number solutions. You say, wait, why are you telling me that? That's all we've been looking for. Well, when you look at 7.7, the lecture after this, we're actually going to expand our number system so that there's other things out there other than just real numbers. So we are looking for real number solutions. So it's a good time to, I think, in mind, come over here. I'm just going to move this over here. You can always go back and rewind it and write that down. And let's actually take a look at the polynomial that's under the radical sign. This is some real number. When I plug in x, x will be a real number, and the output will be a real number. But that real number output has to be greater or equal to 0. So I'm going to go ahead and solve this inequality. Why? Because the square root of a negative number is not a real number, and we're looking for real number solutions. So I'm going to solve this inequality. This gives me 2x is greater than or equal to 3. And now I'm going to divide both sides by 2. So that means whatever value of x I get, it has to be greater than or equal to 3/2. If it's not greater than or equal to 3/2, I can immediately throw it away. So let's go ahead and solve this solution using the power rule. So the index of this is 2. So recall, when I have the radical sign and I don't write an index, the unwritten index is 2. So to get it out from under the radical, or to remove the radical, I raise both sides. I use the power rule, and I raise both sides to the power of the index. In this case, we're just looking at square root, so the index is 2. So the result over here is this becomes just 2x minus 3. It escapes the radical, so to speak. And this becomes 81. So now I'm just going to solve it. 2x is equal to 81 plus 4. So that gives me 2x plus 3, sorry. I'm anticipating the answer. Plus 3. So that gives me 2x is equal to 84. And when I divide both sides by 2, that gives me x is equal to 42. And 42 is clearly greater than or equal to 3/2. But let's just do a quick check. The book always wants you to check. So let's go back to my original equation. And let's put 42 in for x. So that gives me 2 times 42 minus 3. Well, that's equal to the square root of 84 minus 3, which is equal to the square root of 81, which is equal to 9. So it checks. So x is equal to 42 is our only solution. So let's look at another one. So this is example 2. So we're going to do two things to solve example 2. It's not really difficult. So here I have a radical. It has index 2. It's a square root. So what I always want is the radical on one side and everything else on the other. So I'm going to move this term over here. I'm going to move it over here in my next step. So that's going to give me minus 10x minus 1 is equal to minus 3x. So again, let's kind of get some idea of what values of x I can get by taking minus 10x minus 1, and whatever values of x I place in there, it has to be greater than or equal to 0, because we're only talking about real valued solutions. So I'm going to solve that, and this is a good review on solving inequalities. So minus 10x is greater than or equal to 1. I just added 1 to both sides. And now what I'm going to do, I'm dividing through by a negative. And when I divide through by a negative, I have to flip the direction of the sign. The negative stays there. So x is less than or equal to, I'll write that a little bit better, x is less than or equal to minus 1/10. So if we do not find an x that is less than or equal to minus 1/10, I can immediately reject it. So let's continue on solving this equation. So I'm going to square both sides. It's all under the radical. Give me some more room. So when I square the left-hand side, the radical is removed. And minus 3x squared is minus 3 squared, which is 9. And x squared is x squared. So this is a quadratic equation. So I suspect I'm going to get two solutions. I'll have to check both of them. So remember, given a quadratic equation, for you guys, there's only one game in town to solve it. When you go on to college algebra, you'll actually be introduced to the quadratic equation. It's a formula that you can just plug in values. But if we have ax squared plus bx plus c is equal to 0, then we have to factor the side that's not equal to 0, and then we set each factor equal to 0, and that's our answer. So what I'm going to do is I'm going to set each side equal to, I'm going to set this equation equal to 0 by moving the minus 10x over, so it becomes 10x, and the minus 1 over, and it becomes 1. So we have to factor this. So let's come over here and factor it really fast. So I have to have a 9x squared, then my constant term, and then my 10x. Then my constant term, let's start here, because there's only one choice. That has to be a 1 and a 1. And up here, I could put 3x times 3x, and that'll give me 9x squared, or 9x times x. And clearly, looking ahead, my 9x and my x is what I need. So now when I multiply down, I get 9x plus 1, and that gives me 10x. So notice everything's satisfied. 9x times x gives me 9x squared. 1 times 1 gives me 1. 9x times 1 gives me 9x. X times 1 gives me x. And 9x plus x gives me 10x. So my factorization is this. So my factorization is 9x plus 1 times x plus 1, and that's equal to 0. So what do? I set each of these factors. This is factor 1, and this is factor 2. So I set factor 1 equal to 0. So that gives me 9x is equal to minus 1. So x is equal to minus 1/9. So that's one possibility. Setting my next factor equal to 0, x plus 1 is equal to 0, gives me x is equal to minus 1. So for right now, I'm just going to use this as both a necessary and sufficient condition. So is minus 1/9 less than minus 1/10? Yes. How do I know this? Let's do a review. Minus 1/9. Here's my box. I don't know. Minus 1/10. So you cross multiply. So 10 times minus 1 is minus 10. 9 times minus 1 is minus 9. So minus 9 is greater than minus 10. So that tells me the answer to my question. It tells me that minus 1/9 is less than minus 1/10. So this value of x satisfies this criteria. So that's going to work. Is minus 1 less than minus 1/10? Sure. Because if I do my number line, right here is 0, right here is minus 1, and minus 1/10 would be about right here. So both of these solutions work. So I have two solutions to this equation, and those solutions are x is equal to minus 1/9, or x is equal to minus 1. So ideally, you would want to go in and you would want to plug them in, but that's an awful lot of work, and we're getting toward the end of the semester, and this is hard enough. So we're going to assume that this is both a necessary and sufficient condition. Without actually stating that it is, because I have not sit down to try to prove it, and I don't remember if such a proof exists. So we're going to pretend like it is both a necessary and sufficient condition. And it probably is, at least for index of even numbers. Oh, well, you need to see the next one, don't you? So our next one is, look, our index is 3. So, I keep hitting the wrong button. Here we go, index 3. So let's solve this one. So this is example number 3. So I have an index 3 of x plus 1 plus 5 is equal to 3. Now here's the important thing. Since my index is odd, the number underneath the radical, there's no restrictions on it. It can be negative or positive. So that means we're going to have to do a check. That's what it means. So let's definitely do a check. Not quite there, ready yet. So what I'm going to do is I'm going to cube, well, not yet. You have to do one thing before I get ready to cube both sides. I have to move the plus 5 over. So plus 5 becomes minus 5, and 3 minus 5 is minus 2. And now in my next step, I cube both sides. You can already tell right here that my x plus 1 has to be negative, but we'll just check our answers. How's that? Rather than give you a lot of additional rules, I'll just allow you to check them. So cubing the left-hand side gives me x plus 1. And over here, minus 2 times minus 2 is 4 times minus 2 is minus 8. So this is going to be easy to solve. X is equal to minus 8 minus 1. So x is equal to minus 9. So let's see if that works. We have to go up to the original equation. So let's look at the cube root of minus 9 plus 1 plus 5. And let's see if that's equal to 3. If it is, we're done. So that's the cube root of minus 8 plus 5. But the cube root of minus 8, well, minus 8 is equal to minus 2 cubed. So that's minus 2 cubed plus 5. So the cube root of minus 2 cubed is minus 2 plus 5, and minus 2 plus 5 is equal to 3. So my final answers match. Three is what I have, 3 is what I wanted. So the end result is my only solution is x is equal to minus 9. So my next question, I think what I have done with this one is for my other class, I've gone through and I have simplified this greatly. And I'm fine to simplify it, but I've got to check the homework to make sure there's a certain type of problem. Nope, it's okay. I take everything back. I was just worried about something. So let's do the square root of 4 minus x is equal to x minus 2. So again, I'm going to square both sides, but let's just take a quick look at what my solutions have to be. 4 minus x has to be greater than or equal to 0. So that means 4 is greater than or equal to x, or if you want, you can say x is less than or equal to 4. Both of these say the same thing. It says 4 is greater than or equal to x, which is identical of saying x is greater than or equal to 4. So if you have your number line, and right here is 4, then my values of x include 4, and they have to be less than 4. So as customary, we're going to square both sides, because my index is 2. So this gives me 4 minus x is equal to x minus 2 squared is x squared minus 4x plus 4. Again, a quadratic solution is presenting itself. Here's my x squared term. So I've got to bring all of these other terms over. So my minus x comes over, becomes plus x, and my 4 comes over and becomes minus 4. So x squared minus 4x plus x is minus 3x, and 4 minus 4 is 0. So thankfully this is going to be really easy. The first thing we do when we factor is we look for our greatest common factor, and there is a greatest common factor of these terms, and that is x. So x times x minus 3, all of this, once I moved all of these over, it becomes equal to 0. So that means x is equal to 0. That's my first factor. Or x minus 3 is equal to 0, which implies x is equal to 3. Notice that x is equal to 3 and x is equal to 0 are both less than 4. So I think I'm going to answer my question right here. Let's check both of these answers. So we have one answer is x is equal to 0 or x is equal to 3. These are my possible answers. So it's not a theorem. So that's not a necessary and sufficient condition. It's just necessary. So both of these are less than 4. So I can't exclude any of them by this criteria alone. But this is not the only criteria. Let's go up. Let's plug in x is equal to 0 to the original. So the square root of 4 minus 0, is that equal to? That's our question mark. 0 minus 2. Well, the square root of 4, is that equal to? Minus 2. Well, 2, the square root of 4 is positive, is not equal to minus 2. So 0 is not a solution. So we have to check the other one as well. We have to check both of them even when the index is true. So the skinny on this is the only thing you can use with this information is to exclude any possible solutions. If it does not exclude any possible solutions, you still have to check them, which means in the other problem, we should have checked both of them. And you can check them on their own and you'll find out that they both work because I did check them earlier. So now we're going to check x is equal to 4. So 4 minus 4. So I'm plugging in x is equal to 4 to my original equation. Is that equal to 4 minus 2? Why am I doing x is equal to 3? I'm supposed to be checking x is equal to 3, not x is equal to 4, people. Makes a big difference. So I'm checking the x is equal to the 3. So is 4 minus 3, the square root of 4 minus 3, equal to 3 minus 2? Well, the square root of 4 minus 3 is the square root of 1. Is that equal to 1? Yes. 1 is equal to 1. Check. So my only answer is the second answer. X is equal to 3 is the only answer. So the takeaway from here is when we do this over here, all it tells us, it's important information. If x is not less than or equal to 4, there's no way it can be a solution. But in this case, both of our possible values of x, which was this was a possible value, and this was a possible value, but both possible values still didn't work. One was still excluded. So I can only use this to exclude values, not to include them. Okay, now the next one. And so notice here, it is not going to be on your test, but we're going to do it anyway. This is one of the examples of one, especially since we're doing all of this online, that I'm not going to put on the test, but it's good to work through an example. So this is example 5. Because you might see this in college algebra. So we're going to do the square root of 2x plus 5 plus the square root of 2x is equal to 3. And what you want to do is you want only one radical on one side of the equation. So I can actually, this is what I think is worthy of doing. Let's look at our possible answers. We have to have 2x plus 5 greater than or equal to 0, and we have to have 2x greater than or equal to 0. So solving this equation, that implies 2x is greater than or equal to minus 5. So x is greater than or equal to minus 5/2. And over here, this equation tells me that x has to be greater than or equal to 0. Since both of these conditions must hold, then it tells me, if you want to do your number line, this is the only thing really that I want the takeaway, because this is a review of compound inequalities. So let's do the review of compound inequalities. So here is my 0, and here is my minus 5/2. So in one instance, x has to be greater than or equal to minus 5/2. So that's everything over here. And in my other instance, x has to be greater than or equal to 0. So since both of these have to be true, then x has to be in this area up here, which means x has to be greater than or equal to 0, because the and means I'm taking the intersection of two sets. In particular, again, this is the only thing I think that for this review, this tells me that x is in the set. The reason I'm going through this is because this will be something that might very well be on your final. This says x is in the set of minus 5 halves to infinity. And this says x is in the set from 0 to infinity. And the and tells me that you're taking the intersection. In the intersection of those two sets, we just figured out graphically, is equal to the set 0 to infinity. So just a little reminder. So if x is not greater than or equal to 0 when we're finished with this, we can be done. And I'm just going to kind of work through this to show you what all is involved. So my second step here is I have to isolate one of these radicals on one side of the equation. So that means I'm going to take this radical here and move it to the other side. So the next step is I'm going to square both sides. And you're going to see it's going to work out great for the left-hand side, but I have to just square the entirety of both sides. Not each thing individually, but the entirety. So the square root of 2x plus 5 is 2x plus 5. This squared, as I'm using the formula I'm using the formula not a plus b, using the formula a minus b squared is equal to a squared minus 2ab plus b squared, where a is equal to 3 and b is equal to minus 2x. So this is equal to 9, 3 squared, minus 2 times 3 times the square root of 2x plus the square root of 2x squared. So let's simplify. 2x plus 5, I'm not doing anything over there. This is 9, 2 times 3 is 6, times the square root of 2x, and the square root of 2x squared is 2x. Well, that's kind of nice, isn't it? Because when I go to simplify this, I have a 2x on this side and a 2x on that side. So if I subtract 2x from both sides, that's going to give me 5 is equal to 9 minus 6 over 2x. I hope you can kind of see the direction this is going to be going. So what I'm going to do is it doesn't really matter. So I guess I'll just move the 9 to the other side. 5 minus 9 is equal to minus 6 on the square root of 2x. So that's minus 4 is equal to minus 6 on the square root of 2x. Then I'm going to square both sides. So minus 4 squared is 16, and minus 6 on the square root of 2x squared is minus 6 squared times the square root of 2x squared. Students constantly mix this up and say it's minus 6 or 6 times 2x. So I have 16 is equal to 36 times 2x. So 16 is equal to 72x. So x is equal to 16 divided by 72, which is equal to 2/9. So not so bad in the end, and 2/9 is clearly greater than 0. And when you go back in and you plug that in, and we're not going to plug it back in, but you have to, you find out that this works after checking. So in other words, it wasn't a value that I could exclude because I already knew by previous work that x had to be greater than 0. And indeed, my value of x was greater than 0, but you still have to check, and we learned that we still had to check from the previous example. So one last question. We're going to use the Pythagorean Theorem. You'll be surprised at how using the Pythagorean Theorem is useful in actual real life. So let's just review really fast the Pythagorean Theorem. So the Pythagorean Theorem says, I want that color, you have to have a triangle. I grabbed the wrong thing. You have to have a triangle way too big. I'll probably do. You have to have a triangle that is a right triangle, which I'm trying to draw right here. So a right triangle is a triangle whose angle is, largest angle is 90 degrees. And we often indicate that by a little bitty square box right here. And if this is the legs, so the side across from the 90-degree angle is called the hypotenuse. So if A, B, and C represent the legs, then by a theorem of Pythagoras, we have A squared plus B squared is equal to C squared. And forgive me if we just barely reviewed that in a formal lecture. I'm doing so many lectures I can't remember which class I just reviewed this with or not. So this is a reading problem. So find the length of an unknown leg of a right triangle if the length of one leg is 4 meters and the length of the hypotenuse is 10. So that means we're just going to say arbitrary, say, well, A is equal to 4 and the hypotenuse is equal to 10, and this is our unknown. So we start with A squared plus B squared is equal to C squared, but A is equal to 4, B is my unknown, and C is equal to 10. So 4 squared is 16. 10 squared is 100. So I have B squared is equal to 100 minus 16. So B squared is equal to 84. So 84 is a positive number, and since this is a length, B has to be, for it to make any sense, greater than 0. So I'm going to basically take the positive square root of both sides. So that's going to give me B. The positive value of B is equal to the square root of 84, and this is the exact answer. So if you want to know how much that is on the number line, you have to get a calculator out. Or of course we could have reduced this and do a factor tree, 84 to 42, 2, 21, 3, and 7. So let's go ahead and at least do that. So B, 84, is equal to 2 squared times 3 times 7. And all we care about is the squares in this case. So it's 2 squared times 21. So B is 2 squared times 21, which is equal to, I can move, since the index, the power here is equal to the index, the base can be removed out from under the radical. So that's the same as 2 times the square root of 21. So that's it for 7.6.